Welcome, student. In this video, this is the part 3 of stiffness matrix method. In this video, we'll see how to do the analysis of a continuous beam using stiffness matrix method. So in all, there are 5 steps are there. So first 3 steps are to, so in this, we will generate 3 matrices. First is, in the first step, we'll develop the first matrix, that is a displacement matrix. Number 2 is a load matrix in step number 2. And in step number 3, we will develop a stiffness matrix. And then after developing these 3 matrices, then in the step 4, these 3 matrices are connected by using one equilibrium equations, that is load matrix plus K into K matrix into delta matrix is equals to 0. Then at the step number 4, so whatever the unknown displacement at the joint, we able to find here. And then after knowing the unknown displacement, then in the step number 5, using slope deflection equation, the unknown end moments we can able to find. And then after knowing the end moments, then shear force and bending moment is the step number 6. So here the first step, that is generation of the this displacement matrix. So in the displacement matrix, first of all, determine the degree of freedom of the given structure. So degree of freedom, what is the degree of freedom, that I will explain in the example itself. So elements in this particular matrix is the unknown displacement at the respective coordinates, is the first matrix. Number 2 is a force matrix. So in the force matrix, so actually they will determine the fixed moments. Then fixed moments are at the respective coordinates, selective coordinates are the elements in the load matrix. And we know in the case of stiffness matrix, in this case, the unit deformation is applied at the respective coordinates. And then because of this, whatever the unknown forces are the elements in the stiffness matrix. So in the example, we will see these particular steps in detail. So we'll take the first example. So this is the continuous beam, 2-span continuous beam. The first part is AB span. It is a 5 meter subjected to point load 50 kilonewton. And second span, it is a 3 meter subjected to uniform distributed load of 20 kilonewton meter. So what is the question? Analyze this beam using stiffness matrix method and draw bending moment diagram. Okay, now in the step number 1, we will determine the degree of freedom, because we will first of all determine the, we'll generate the displacement matrix. So to obtain the degree of freedom, so the loads are not required. So remove the load from the structure and only consider the structure. Then what is the degree of freedom? So degree of freedom is nothing but what are the possible displacement at the joints, what are the possible displacement at the supports, are the degree of freedom of that particular support. So for 2D structure, for 2D frame, 2D structure, so there are 3 possible displacements. The displacement may be in the horizontal direction, displacement may be in the vertical direction, and there may be a rotational. So there are 3 possible displacement at every support, at every the nodes or joints. Now here, the first joint is this. It is a fixed support. Now fixed support, out of these 3 possible displacement, any displacement is not possible, because fixed support is restrained in all 3 directions. So degree of freedom of this fixed support is 0. Then coming to support number 2 now. So it is a roller support. Actually, roller support offers one reaction, that is vertical reaction. So therefore, vertical direction is restrained. So not displacement in vertical direction is not possible, but 2 directions are free. Other 2 directions are free, that is horizontal displacement and the rotation is possible. But if in this example, both loads, that is 50 kilonewton and 20 kilonewton, this is acting in the vertical direction. So therefore, this horizontal degree of freedom, it's not necessary to be considered, because horizontal displacement is not possible. So we will consider, so or it is always considered one degree of freedom, that is a rotation. So at B support, one rotational degree of freedom is possible. That is number one. Similarly, at support C now, it is hinge support. So hinge support offers two reaction. One is vertical reaction, and next is a horizontal reaction. So these two reactions, in the sense resistive forces, so this is restraining forces. So therefore, vertical displacement as well as horizontal displacement is not possible. So only free is the rotation. So at C point also, the degree of freedom is the rotation. So in all, in this particular structure, two degree of freedoms are possible. One is a rotation at B point, and rotation at B point, and rotation at C point. Okay, now these rotations are the unknown displacement at support B and C. Now give the numbers. Okay, give the numbers. So first of all, we'll give this rotation degree of freedom as a number 1 at B point, and this particular as a number 2. So these are the two coordinates. Okay, so this is coordinate number 1 and this is the coordinate number 2. Okay, now we can easily write the displacement matrix. It is denoted by delta matrix. So it is equals to now this is the displacement, unknown displacement at coordinate 1. So coordinate 1, what is unknown displacement? Theta b is the unknown number 1. Then this is a second element is a unknown displacement at second coordinate. Thus at second coordinate, unknown displacement is theta c. So in displacement matrix, there are two elements. First element is a theta b, unknown displacement at coordinate 1, and unknown, the second element is unknown displacement and theta c. Call this equation number 1. Next, second, now we'll generate the second matrix as per the step number 2. It is called as a load matrix. So to calculate the element in the load matrix, or to develop the load matrix, determine the fixed end moment, what is called as a restraining forces, restraining moments at the support. Okay, so to calculate the fixed end moment, and we know that to calculate the fixed end moment, we do the assumption that each span is assumed as a fixed beam. So given structure, it is a two span continuous beam. So therefore, there are two span. First span is subjected to a point load of 50 kilonewton. 50 kilonewton. So this is a case of fixed beam subjected to point load. So this distance is A, and this distance is B. So here this is 3 meter is there, and this is 2 meter, and this is equals to 50 meter, 50 kilonewton. Then what is this fixed moment? That is M AB. So this fixed moment is a hogging nature. Okay, and what is the fixed moment here? This is also hogging nature, acting from the bottom. Okay, now what is the formula to calculate this moment? So formula is here. So it is W AB square by L square. WAB square by L square, and this is minus because this moment is anti-clockwise. Then next is this fixed moment. This is AMBA. Since it is a clockwise, therefore this is a plus. And what is formula for this? WA square B divided by L square. So it is a 36. This is for the first span. Now for the second span, so it is a BC span is there. So there is a uniform distributed load. So what is the fixed moment here? It is hogging nature, anti-clockwise direction, and this is a clockwise direction, also hogging nature. Then it is a fixed beam subjected to UDL. So this moment will be equal to MBC moment. So it is a minus WL square by 12. So its answer is minus 15. And this moment will be equal to plus WL square by 12. So it will equal to 15. So these are the fixing moments to be calculated. So in this figure also, these moments are shown. So this is the fixing moments at A support. These are the two fixing moments at the B support, and this is at the C support. Then we can write the element in the load matrix. Okay, now this is the load matrix. Okay, now here there are two elements. So this element is fixed end moment or restraining moment at coordinate 1. Our coordinate 1 is at B. So this is a location for B. So how many moments are there? So this is a common joint is there for both spans. So there are two moments. First is a clockwise moment 36 and anti-clockwise moment 15. So 36 and anti-clockwise minus 15. So the first element is 21. Then our second coordinate is here. So it is a plus 15. So this is a second element. So equation 2 is a load matrix in which there are two elements. One is at coordinate 121, coordinate 2, it is 15. So this is a matrix number 2. Then third is now we will generate the stiffness matrix. So actually part 2, stiffness matrix part 2, we have discussed in detail how to generate the stiffness matrix. Since this is the first example, therefore here itself, here also we will discuss how to generate the stiffness matrix. This is a given structure in which there are two coordinates are there. So since there are two coordinates, so therefore size of the stiffness matrix will be equal to 2 by 2. So there will be 4 elements. In the first column, 2 elements. In the second column, there will be 2 elements. Now we'll generate the first column of the stiffness matrix. So write a line to generate the first column of the stiffness matrix. Apply unit deformation at coordinate 1. At coordinate 1. So here this is a coordinate 1. So before applying unit deformation, first of all, apply fixity at the ends of the each part. So this is A, support, provide fixity here, restraint here. At B, provide restraint. At C, provide restraint. Now apply unit deformation at coordinate 1. Apply unit deformation at coordinate 1. What is our coordinate 1? Is a rotation. So here apply a rotation at coordinate 1. Apply a rotation. So when we apply the rotation in a clockwise direction, so the second span, so this particular span, so the moment is acting from the top. So therefore it will deform downward. Similarly, we will continue this arrow in a clockwise direction so that this particular clockwise moment, which is applied at B, so this is acting from the bottom on the first span. So therefore, since it is acting from the bottom, therefore it will be hopped like this. So these are the deformations in the first span and second span. Then, so this, when we apply the unit deformation at joint B at coordinate 1, so it will produce a internal forces. Now we will try to calculate the internal forces. We'll try to calculate these internal forces in each part separately. This is the first part is there. This is the first part, and this is the deformed diagram. So show here the deformed diagram, and then here actually this is the now while applying this moment, how much moment is required to apply the moment such that it will produce a slope equal to 1. Okay, so the first part is this, which is deformed like this. So here draw the tangent, and this slope of this tangent must be equal to 1. So that is theta b value must be equal to 1. Now to produce theta b equal to 1, that is slope at B point equal to 1, how much moment is required to apply here at this point? We have applied a moment, but how much magnitude of the moment is required to apply so that this moment will be, this slope will be equal to 1. So it will be equal to, it is standard formula, it is 4 EI divided by L. So 4 EI divided by L, length of the this first part is 5. Okay, in a clockwise direction. Then at the far end, the moment produced will be half of this. This is because of carryover theorem. So it will be equal to 2 EI divided by 5. Okay, so these are the two end moments. Both are clockwise nature. Okay, now this is a, now this will produce anti-clockwise couple. Okay, now two forces will be generated at the ends for equilibrium purpose, for balancing purpose. So these two forces are, this is called as a balancing couple. It is called as a balancing couple. Now, whatever these movements develop at the ends, these are clockwise nature, and therefore balancing couple is in an anti-clockwise direction. So therefore this force will be in a downward direction, this force will be in the upward direction. And what is the value of this? How this value is? It will be equal to m divided by L. It is called as a magnitude of the couple. So m is nothing but imbalance moment. So what is here at B support here? What is the moment? It is 4 EI by 5. And this is also clockwise. At A support, it is 2 EI by 5. What is, both are clockwise. Therefore, directly there is addition. So 4 plus 2, it is 6 EI by 5 is the value of this. 6 EI by 5. Okay, divided by EL is again 5. So how much it is? Here it is written. It is 6 EI by 5 divided by 5. Its answer is 0.24 EI. And this also will be 0.24 EI at A support. Thing is that only thing, this is a downward, this will be upward. So these are the internal movements. These are the movements at the end and resisting couple or resistive forces at the end in the part first. Then in the similar way, the moments and moments at the ends and the resistive couple magnitude is determined in the second part. Now second part is deformed in a downward direction as shown here. So this is deformed shapes is shown here. Now, so what is the slope here? So theta B. So now apply the moment, we have applied the moment at B point. Now apply in a clockwise direction. Now how much moment is required to apply? It will be equal to 4 EI by L. Now length of this span is equal to 3. Okay, so that it will produce a slope equal to 1. So at this joint, B joint, moment will be 4 EI by 3, and at the far end, it will be half of this. It is 2 EI by L. Okay, so these are the moments at the ends. Okay, then this will produce a resistive couple. This will produce a resistive couple. Again, what is the magnitude of this resistive couple? It is m divided by L. So it is 4 plus 2. It is 6 EI divided by 3 divided by 3. So its answer is coming 0.67 EI this force and 0.67 EI this force. Now this is these movements are, whatever the end movements are there, it is clockwise nature, and therefore whatever this resistive couple, it must be anti-clockwise. So therefore this force will be downward, this force will be upward. Okay, now these are the movements at the end and resistive couple in the part 2. Okay, now we can write the element in the stiffness matrix in the first column. Okay, the first element will be K11. K11. What is K11? Stiffness at 1 due to unit deformation at point 1. Stiffness at 1. Stiffness in the sense force required to produce a unit deformation. So what is a force? What is a force at coordinate 1? Now our coordinate 1 is what? Our coordinate 1 is a movement. Our coordinate 1 is a movement, and coordinate 2 is also a movement. So at coordinate 1, what is the total movement produced? So is the element number 1. So in the first part, at coordinate 1 is here. What is moment? What is this moment? 4 EI by 5. And its direction is clockwise. Its direction clockwise, and assigned coordinate 1 direction is also clockwise. So it will be positive. So this is the first. Then in the second part, this is the moment produced at B point at the same location. So again, it is 4 EI by 3. What is direction? Clockwise. And coordinate 1 is also a clockwise. So both are positive. So addition of this, it is equals to 2.13. Then stiffness at 2 now. Now our coordinate 2 is a moment. So at C location, this location, what is the moment? Moment produced. So how much it is? 2 EI by 3. And it is a clockwise moment is there, and our coordinate 2 is also clockwise. So how much it is? 2 EI by 3. So it is equals to 0.67 EI. So this is the first column of the stiffness matrix. Now we'll generate the second column of the stiffness matrix in the similar way. So to generate the second column of the stiffness matrix, apply unit deformation at coordinate 2. This is our structure. This is support A, this is support B, and this is support C. First of all, provide a restraint at A support, B support, C support. And then what is coordinate 2 is a moment. So at C point, apply the moment. Apply the moment. How to apply? In the direction of coordinate 2, in a clockwise direction. So therefore, only the second span will differ. Since here we have provided the restraint, first span will not be differ. Only second span will differ, and the moment is acting from the bottom. Therefore, this span will going to hop. It is going to hop. And how much moment to be applied? What is the magnitude of this moment? Apply the moment in such a way that this slope will be equal to 1. Theta c value must be equal to 0. Then calculate the end moments and restraining couple value. Okay, so this is since only the second span is deformed. So therefore, show the forces here in the second part. So this is the deformed shape. Then this is the moment required to produce a unit slope. So here it is required to apply 4 EI by L, that is 3 meter. And at the far end, how much moment will be produced? According to carryover theorem, it will be half of this. So 2 EI by 3. Okay, and now here the resistive couple, that is forces, also generate. Okay, see here, but in the figure it is not shown because there is a reason. What is that reason? So see, so this is a clockwise movement, this is a clockwise movement. So resistive couple must be anti-clockwise. So this must be downward and this must be upward. This must be upward. And what is the value of this force and this force? Okay, so this will be lever arm. Okay, so what is the value of this? EM by L. So it is 4 plus 2, just addition of this, both are clockwise. 4 plus 2, 6 EI divided by 3 will be the value of this. But in the stiffness matrix, these elements, these forces are not required. Okay, because both coordinates, coordinate 1 is also a moment and coordinate 2 is also a moment. So it is not coordinate 1 as well as coordinate 2 is not a force, these are moments. So only in the figure, the moments are whatever the required part, moment required, therefore moments are only shown. So in the figure, it is not shown. It doesn't mean that the resistive couple is not developing. It is developed. Then the element, first element in the second column. So it is K12. That is stiffness at 1. Stiffness at 1 due to unit deformation at 2. Stiffness at 1. Okay, so at coordinate 1, our coordinate 1 is a movement. So at coordinate 1, what is the movement produced? How much it is? 2 EI by 3. And what is the sign for this? Okay, see, the coordinate 2 is a clockwise and the moment produced is also clockwise. Therefore, this is plus. So it is 0.67 times EI. Okay, then stiffness at 2, K22. Stiffness at 2 due to unit deformation at 2. Then stiffness at 2 due to unit deformation at 2. Now, at 2, what is the moment is 4 EI by 3. This is clockwise. And our coordinate 2 is also a clockwise. So moment produced will be 4 EI by 3 plus element, and its answer is 1.34. Okay, so these are the two elements in the second column of the stiffness matrix. So this is equation 3 is the required stiffness matrix. So just apply the properties, whether it is a correct or not. So it is a square matrix is the first property. There are 2 columns and 2 rows are there. Number 2, stiffness matrix is the symmetric matrix. So therefore this element, so it is a K21 must be equal to K12. So it is there. Okay, so second property is also satisfied. And third, the element lying in the leading diagonal is always positive. So this element and this element K11, K22 must be positive. Now it is coming. So therefore, whatever the equation 3 stiffness matrix is the correct one. Then in the step 4 now, what are the 3 matrices developed? Just connect it by using a equilibrium equation. So this is the load matrix plus K matrix into delta matrix is the equal to 0 is the equilibrium equation. So this is a load matrix, equation number 2, plus it is a K matrix. So this is a K matrix, that means equation number 3 into displaced matrix is equation number 1 is equals to 0. Okay, now first of all, do multiplication between this K matrix and delta matrix, and that is whatever this equation convert into simultaneous equations, two equations. Okay, so the first is first element, how to do the multiplication. So this element 2.13 EI into theta b plus 0.67 EI into theta c is equal to, now whatever this element value mine is 21, take on the right side, so it will becomes minus 21. Call this equation A. Okay, then second 0.67 EI into theta b plus 1.34 EI into theta c is equal to, now they take this 15 on the right side, it is minus 15. Call this equation B. Now equation A and equation B, these are the two simultaneous equations in which there are two unknowns, EI into theta B and EI into theta C. So solve these two simultaneous equations for EI into theta B and EI into theta C. So we get two values as EI into theta B is equals to minus 7.56, EI into theta C is equals to minus 7.41. Now here, this is the end of step number 4. So here we are able to determine the two unknown displacement at theta B and theta C. Now these answers of both unknowns are negative. What it means that whatever the assumption made regarding the nature of this rotational displacement is opposite. What it means? So here we have assigned first of all coordinate 1. So here this is theta b. We have assumed theta b here as a clockwise. Theta c at coordinate 2, we have assumed it is as a clockwise. So that is theta b and theta c, we have assumed both as a clockwise. But the answer is, because these are the unknowns, so at this stage it was not known whether the displacement at rotation displacement at coordinate 1 and 2 are positive, that is clockwise, or anti-clockwise. It was not known, therefore we have made this assumption that is both are clockwise. But after making this assumption, when the answers are determined, both are found to be negative. That means our assumption is wrong. So here, whatever the unknown displacement at 1 and 2 are not positive, they are negative in the sense they are anti-clockwise. So slope at B point and C point are anti-clockwise. Then after this, step number 5. Now here in the step number 4, we have determined the unknown displacement, theta B, theta C. And then to find the final moments at support A, B, C, D. Okay, A, B, C, we will use the slope deflection equations. Only this is the option. Then using slope deflection equation. So we know that slope deflection equation for every span, there are two slope deflection equation. So this is the first slope deflection equation for moment EM AB. So it is 2 EI by L, 2 theta A plus theta B minus 3 delta by L minus EM AB. Okay, so this is the slope deflection equation for this particular moment. So here substitute value, it is 2 EI by L, span of this first span is 5 meter. Now 2 theta A, slope here, since this is a fixed support, slope will be equal to 0, plus theta B keep as it is, minus delta here in this equation is the level difference between A and B. So there is no level difference. So therefore delta value is 0. So this value will be 0. And then this is the initial friction moment. So already this MAB is calculated we have. So what is value of MAB? MAB value is how much? It is minus 24 is the value. MAB is minus 24. So write that value as a minus 24. So this is a minus 24. Then simplify this, and then EI into theta B value. EI into theta B value already it is known. We have determined here EI into theta B is minus 7.56. So substitute value EI into theta 6. Then we get the value of MBA as a 29.95. Sorry, this MBA. So MBA already this value will be equal to, this value will be 27.0. So it is a minus, that is anti-clockwise. So this movement is acting anti-clockwise, and therefore nature is hogging nature. Similarly, write the equation for MBA now. So equation is 2 EI by L, 2 theta B plus theta A minus 3 delta by L plus MBA. So MBA is determined already in above step. So its answer is plus 36. Delta value 0, slope at A point is 0. So only remains is EI into theta B. So EI into theta B substitute value. So it is a minus 7.56. So here this answer is coming. Okay, so now this answer is, this moment is coming as a 29.95. So this is at which point? At B point now here. Okay, so this moment at B point, so it is clockwise. Plus in the sense this is acting clockwise, therefore nature is hogging nature. Then again now, take the now next span. So now B to C now. So this is a fixed support, this is a fixed support, this is a continuous support here, and this is a end support. Okay. Now write a slope deflection equation for MBC span. MBC span. Now we can write a modified slope deflection equation. So write a modified slope equation for MBC. So this is the equation 3 EI by L theta B minus delta divided by L minus 1/2 MCB plus MBC. Then substitute the value in this equation. Then we get the value to be equal to minus 30.06. Minus 30.06. Okay, so there is a, actually there is a movement here. This answer is a minus. That means here this movement is in anti-clockwise direction. It is anti-clockwise direction. Now this movement, that is MBA movement, is at 29 point. How much it is? 29.95. And MBC, by this calculation, it is find out to be 30.06. 30.06. So actually, the summation of this moment and this moment must be equal to 0. So there is a slightly variation in the whatever the values. So therefore, for more correctly, we will consider this to be a again equals to minus 29.95, because the difference is very, very negligible. So assume this particular value to be as a minus 29.95, so that this summation will be exactly equals to 0. Then, so the nature as well as the values are determined of the end moments. Then the plot the bending moment diagram. Bending moment diagram. So now use of the slope diffraction equation is not the scope of this particular video. Just in a superficial way, I have explained this slope diffraction, the equations. Otherwise, our objective, basic objective is of this particular video is to explain the stiffness matrix method and how to find the unknown displacement. Then once the unknown displacements are determined, then by using slope diffraction equations, determine the end moments and then draw the bending moment diagram. Okay, so this is the end of this particular example. So thank you for patient listening. Then in the next video, I will explain the next part of the next example, example number 2. Thank you.